Imagine you're looking up at the night sky. Clear and endless stars scattered like dust across the dark. You think to yourself, I wish I could reach one of them. But you know the distance is immense. The closest star is 4 light-years away. That's 4 years even if you traveled at the speed of light. And by airplane? Hundreds of thousands of years. But what if distance wasn't the only way to get there? What if, in the fabric of space itself, there was a shortcut, a tunnel connecting 2 distant points? You step in here, and emerge there, in an instant. This idea is called as a wormhole. The name sounds strange, I know. But it's just a name. There's no actual worm. No hole in the ground. It comes from an old analogy. Imagine a worm burrowing through an apple, taking a shortcut from one side to the other, instead of crawling all the way around the surface. That's the idea. Instead of traveling across space, you go through it, a tunnel that cuts through the very structure of spacetime. Here's the strangest part, nobody built this tunnel. Nobody discovered it in space. It came from mathematical equations, specifically, from Einstein's theory of gravity, known as general relativity. In this theory, gravity isn't a force that pulls objects. It's the result of spacetime bending around massive objects. Like a rubber sheet curving when you place a heavy ball on it, space bends around stars and planets. And everything moves along that curve, not because it's pulled, but because it's sliding through the dip. In 1935, Einstein was working with a physicist named Einstein-Rosen. They were solving the equations of general relativity, trying to understand the shape of space around massive bodies. And as they calculated, they noticed something strange. The math allowed for a kind of bridge between 2 distant points in spacetime. This bridge doesn't go across space, it goes through it, as if space had folded over on itself, bringing 2 far ends together. They weren't looking for a way to travel between stars. But the math led them there anyway. Theoretically, there could be a shortcut between 2 distant places. This became known as the Einstein-Rosen bridge, what we know as a wormhole. But what does theoretically possible mean? It means the laws of physics don't forbid it, but they don't guarantee it either. Like saying you could build a glass bridge between 2 cities, but nothing ensures it won't shatter. Same here, the math allows wormholes, but there's no proof they actually exist in the universe. To this day, no one has ever seen a wormhole. No telescope has detected one. No spaceship has passed by it. No star orbits an invisible mouth. No strange light distortions point to its presence. All we have is that the idea is mathematically allowed, but no evidence it's real. I know what you're thinking. And I know what really matters to you. If a wormhole formed, could we use it? Not easily. The first problem, even if a wormhole formed, naturally or artificially, it would collapse instantly, in a fraction of a second, before anything could pass through. So how do we keep it open? That's where exotic matter comes in. It's not matter from another planet. It's not magic. It's a hypothetical substance with a rare property. Instead of pulling, it pushes. In physics, we say it has negative pressure or negative energy. This effect could act like a strut inside the tunnel, propping the walls open and preventing collapse. But does this matter exist? We don't know. But in highly precise lab experiments, we've observed something called the Casimir effect. Imagine 2 tiny metal plates placed extremely close together in a vacuum. Even with nothing between them, they're pulled toward each other. Why? Because the vacuum isn't truly empty. It's filled with virtual particles that pop in and out of existence. But between the plates, some of these particles can't form, while outside, they can. This creates a pressure difference, and the plates are pushed together. That pressure difference is equivalent to having negative energy between the plates. So yes, negative energy exists, but it's incredibly weak, confined to microscopic scales. To open a wormhole large enough for a human to pass through, we'd need an amount of this energy equivalent to the mass of an entire star, or more. And even if we could gather it, how would we place it in the tunnel? How would we control it? There's no answer, not yet. You might think that's all. But the real challenges haven't even begun. Let's say we managed to open a wormhole right here on Earth. Where would the other end come out? Can we choose the location? Can we aim it? Unfortunately, no. Wormholes, as described in the equations, don't come with a map or a distance counter. The other end might end up in a distant galaxy, in a place we can't predict, or even in a different time. We have no way to control the direction, the destination, or the environment on the other side. You might step in here, and emerge inside a star, in pure vacuum, or even in another universe entirely. The third challenge? Time travel. Here, things get even more complex. If one end of the wormhole is placed in a region of strong gravity, like near a neutron star, time there would pass slower compared to the other end, which might be on Earth. If one end stays there for years, then is brought back close to the other, time would have advanced differently at each end. For example, someone entering from the slow end, near the star, could exit from the fast end, on Earth, in the past. But this opens a dangerous door, the grandfather paradox. If you travel back in time and kill your grandfather before your parent is born, you'd never be born. But if you were never born, how did you travel back to kill him? Logic collapses. So many scientists believe there's a cosmic law that prevents this kind of time travel. Maybe the wormhole collapses the moment you try, or nature simply forbids such conditions from forming. Like fire can't burn in a vacuum, maybe the universe won't allow travel to the past. Could wormholes be connected to black holes? Some theories suggest a black hole might be an entrance to a wormhole, and whatever it swallows emerges from a white hole somewhere else. But as attractive as this idea is, there's no evidence for it. Black holes, as we understand them, destroy everything that enters. Gravity at their center is so intense it tears atoms apart, crushing everything into an infinitely dense point called a singularity. Nothing escapes, not even light. And the white hole, a theoretical opposite of a black hole, has never been observed. We don't even know if it can exist. If it does, it would be an object that ejects matter instead of swallowing it, but no observations point to such a thing in the universe. Now, I know the question spinning in your mind, and it's a smart, honest one. Why do we even care about wormholes if they've never been seen, and we can't use them? Simply, because studying them helps us test the limits of physics. We're trying to unify Einstein's theory, general relativity, with quantum mechanics. But these two theories don't agree in extreme places. Wormholes, as mathematical objects, sit right at that boundary. Understanding how a wormhole could stay open, or how exotic matter interacts with spacetime, might lead us to a new theory, one that unifies both worlds. A theory that explains everything, from the smallest particles to the largest galaxies. In movies, wormholes are shown as cosmic highways, opened with the push of a button. But reality is far more complex. There's no proof they exist. No technology can create them. And we don't know if nature even allows them. Yet the idea alone reveals something profound. The universe doesn't care what we think is impossible. 100 years ago, people thought black holes were just fantasy. Today, we've seen their shadow. 100 years ago, reaching the moon was a dream. Today, we've stood on its surface. So maybe, in decades, or centuries, a new generation will discover how to fold spacetime, and use it to reach distant stars, not by speed, but by shortcut. In the end, wormholes aren't just sci-fi fantasy. They're a natural consequence of the universe's laws, even if we've never seen one. They remind us that space isn't a flat surface we walk across, but a flexible fabric that can be bent, folded, and pierced. And what we know today is just the beginning. If you found this video meaningful, please hit like, subscribe, and turn on the bell. Because the next journey might be to the beginning of the universe, or to parallel worlds. I'll see you in the next video. Until then, keep asking questions.